Alright, so this video is kind of just a rational function introduction. So it's not really material that we're going to be quizzed or tested over that much. It's just kind of what is a rational function. Well, maybe if the slide changes. There we go. Alright, so I have my parent function, f of x equals 1 over x. So a rational, the word rational in math essentially just stands for a fraction. So a rational function is just a function that's going to have the x in the denominator. For our purposes, it's going to have now there can also be an x in the numerator, but at a minimum, there will be a variable in the denominator. So domain and range, last semester we wrote what x could be, like negative infinity to infinity, or negative infinity to 3, or whatever the domain was. Some of these rational functions can get a little complicated. So instead of writing what x can be, just to make it shorter, we're going to write what x cannot be. So in math, there's something specifically we can never do. And there's really only one thing when we're dividing that we can't do, and it's we cannot divide by 0. So in a rational function, since we have an x in the denominator, any x value that makes me divide by 0 cannot happen. So any value of x that I plug into the equation and it gives me 0 in the denominator, we're going to say for the domain that x can't be, x cannot equal whatever that number is. So if we just have 1 over x, an x value that we would plug in that would cause issues and make us divide by 0 would just be the number 0. So if we plug in a value of 0 into this parent function, we will end up with 1 divided by 0, which is no dice. That's not good. So 1 divided by 0 can't happen. So my domain on this graph would be x can't be 0. Vertical asymptote is a word that we've never talked about. And I know I skipped range. I'll come back to it. So vertical asymptote is a word you may have heard in the past, but we have not talked about it in Algebra 2. So vertical asymptote is, for our Algebra 2 definition, an asymptote is going to be a line that our graph is going to get very, very close to, but never actually touch. So we just talked about we cannot divide by 0. So if x cannot happen, if 0 cannot happen as an x value, then we will not have an x value of 0 on the graph. If we're not allowed to plug in x equals 0, then when we look at our graph, when we approach the x value of 0, and if you look at the graph that's up there, as we approach 0, the graph gets weird. We have this and this. And if we notice, there's a blue dotted line on the x value of 0. So an asymptote is a line that our graph gets very, very close to, but never actually touches. So in this graph, we can't plug in the exact value of 0, but we can plug in like 0.000000001. So we're going to get very, very close to plugging in 0, but it's never actually going to happen. So our asymptote occurs at x equals 0, because that is a line that our graph is going to approach, but we're never actually going to cross that line or touch that line. Range, I'll go to last. So now we're going to move to horizontal asymptote. So there's two types of asymptotes on most of our graphs. Not all of them have a horizontal, but all of them will have at least one vertical. So horizontal is the asymptote that's going to go left to right. So on this, it's following the horizon, if you've ever heard that word, talking about nature. So horizontal asymptote is side to side. And if you look, we have a dotted line at 0. So the horizontal asymptote occurs at y equals 0. Next week, and in a future video, I'm going to discuss exactly how to find a horizontal asymptote. But for now, we're just kind of introducing it, so we're just going to look at the graph, and then we'll go to how to mathematically do it in the future. And if I have an asymptote at y equals 0, that means a y value of 0 will not be happening. So if we have a horizontal asymptote at 0, that means that we will not have a y value of 0 in the range. All right, so another example. So on this graph, we see that the whole thing looks like it has been picked up and shifted to the left. So on our last example, our asymptotes start at x equals and y equals 0. So they both happen at 0. In this graph, if you notice, the horizontal asymptote is still at 0. And we just discussed on the last, if we have a horizontal asymptote at y equals 0, it means a y value of 0 will not be happening. By definition of what it means to be an asymptote, it means that that can't happen by default. So vertical asymptote, it's shifted. And we'll talk about mathematically solving them later, but for now, vertical asymptote's not too complicated. So in math, we cannot divide by 0. So any number, any x value that I plug in, and it forces me to divide by 0, it's going to give me a vertical asymptote. Later, we'll go over something called a point of discontinuity. So there is one exception to this, but we're not there yet. So any x value that causes me to divide by 0 is going to give me a vertical asymptote. So if you look at this equation, we have 1 over x plus 2. So the x value that's going to cause issues is negative 2. And the reason I know it's negative 2 is I have 1 over x plus 2. So if I plug in negative 2 where I see x, then I get 1 over negative 2 plus 2. And then negative 2 plus 2 is 0. So if I plug in an x value of negative 2, it forces me to divide by 0, which cannot happen. So in this case, x cannot be negative 2. And if I will not have an x value of negative 2, then I will have my asymptote at negative 2. And if you look at the graph right here to the right, our vertical asymptote has moved to negative 2. And if I ask you transformation rules from back in the day, if we remember our h, our quote-unquote h value is a liar. So the number next to x, if we see x plus 2, that's my h value. So this x plus 2 means that we're going to move left 2, which we actually see this transformation visually on the graph. All right, so this one's very similar. But if you notice, the minus 2 is not in the denominator with x. So if I'm looking for x values that I plug in and get a value of 0, since there's nothing in the denominator with x, we just aren't allowed to plug in the number 0. And if you look on the graph to the right, you'll see that the vertical asymptote is at 0, so our logic holds. But it's what we plug in for x that causes issues. And since x is all by itself, we're just not allowed to plug in 0. We can plug in any other number we want. If you look at the horizontal asymptote, though, it's not at 0 anymore. It has been moved, just by looking at the graph, it has dropped down to negative 2. And if I have a horizontal asymptote at negative 2, then I know my range value of negative 2 will not be happening. And if we remember transformation laws from last semester, this number out here all by itself at the right of the equation is what we called our k value. And this value moves us up and down. So if we have a minus 2 at the end, we would assume that our graph had gone down 2. And then if we look at the graph, we see that it actually did move down 2. I'm not going to go over domain and range and all that stuff for this one. I just want to talk about exactly what a reflection does in a rational function. So I'm going to draw the rational function we've been looking at in green here. So we had, I'm not an artist, but we had something that looked like that. What I had in green is what we've been looking at for our past 3 examples if you've been writing the graphs down. So when we look at these green graphs here, the negative, last semester, talking about transformation stuff, we talked about how a negative reflects the graph over the x-axis. So when I see a negative, I'm assuming that we're reflecting over the x-axis. And if I look, this green part has been reflected over the x and now looks like that. This green part has been reflected over the x-axis and now looks like that. So in class I use my hands, but obviously you can't see those. So just picture the green part in the top right corner being tumped over or flipped over from the first quadrant to the fourth quadrant. So both pieces here are being reflected, if you were curious how a reflection work with a rational here. Last one, and we'll put it all together here because this has a bunch of transformations. So domain, again, domain is any x value that I plug in and it causes issues. And if you notice, because this graph is kind of big, the scale got all messed up. So these count by 2s. That's a side note. So any x value that I plug in that causes problems, it makes me to divide by 0. So 3 over x plus 2. So there's x plus 2 in the denominator. So that means if I have an x value of negative 2, we have issues. So I cannot, under any circumstance, have an x value of negative 2. So x will not be negative 2. And if we visually look at the graph, I see that I have a vertical asymptote at that value. So since this is our last example, I do just want to make sure, if you've probably noticed this already since I've said it 1,000 times, but the domain and vertical asymptote for now are the same information. I mean, they're always going to be the same with one caveat, that a domain restriction, so an x value that x cannot be, so in this case negative 2, will either be a vertical asymptote or a point of discontinuity. But we haven't talked about a point of discontinuity yet, so obviously that's not what it's going to be. But we'll get to that in the future. But I don't want to lie to you on this video just because we haven't talked about it yet. So the horizontal asymptote, again, for now, we're just going to look at the graph. I'll tell you how to mathematically find it in the future. But if we look at the graph, my asymptote happens at 4. So y equals 4. And if I have an asymptote at y equals 4, then you know that y cannot be 4. And just like domain and vertical asymptote, my range and horizontal asymptote, we know, are the same information. And that will always be true. So if we remember back transformations from last semester, this was my h value. And if I had an x plus 2, then I would assume that the graph would move left 2. And if I look, it moved from 0, where it originally was, to negative 2. So my graph did get picked up and move left 2, so that's fine. What I'm going to highlight in pink was my k value. And the k value we expect to move me up or down. And since I have plus 4, we would assume that the graph would be picked up and moved 4 units up. And my asymptote, my horizontal, should be at 0. But it got moved up to 4. So transformation is just normal. And then this from last semester that I highlighted in green is my a value. This a value causes a vertical stretch or vertical compression. And if we remember that if a is greater than 1, we call it a vertical stretch. And if a is a fraction or a decimal, if it's between 0 and 1, that's going to be a vertical compression. Sometimes you'll see it as vertical shrink, but I like the word compression better. So in this case, 3 is bigger than 1, so we're going to have a vertical stretch. So this kind of is our intro to rationals. It's just kind of what the graphs look like and what general information we can pull just by looking at the graph. So hope this helps.